In this video, we're going to talk about how we find values that are from normal distributions. We're going to be looking at the inverse, basically, of the normal distribution. All right, so previously we were given a normally distributed random variable x. So our variable was normally distributed. We were given the mean and the standard deviation, and we were asked to find the proportion of observations that cover a range of values or the probability that a variable would be within a certain range of value, right? And so what we did is we started with, okay, well, what are one of the endpoints of the range that of the interval that we were given, right? So we start with that value and then we convert it to a z-score by using the formula z equals observation minus mean over standard deviation. And that will give us our z. And then we would use our computer technology to find the area under the curve covering those z values using the p-norm function in R and JASP, right? And that would give us the proportion or the probability that we were looking for. Well, what we want to do now is kind of like flip it and reverse it, right? Now we were going to be given the proportion of observations that fall within a region or that represents the area under a curve. And we want to kind of backtrack to find the x values that align with that area. So we're going to start with the probability or proportion. And then we're going to introduce a new function that converts proportions to actual z values. And that function is known as our q-norm function. It's going to take a proportion or a probability back to being a z. And since we have this formula here that relates x and z, we can basically just solve this equation for x, and we have another formula to get or convert our z back to x, right? And so this is the formula that we're going to use, and it basically comes from solving this normal z-score formula for x, right? Just to show you that real quickly, if I want to solve that equation for x, I need to first get rid of that denominator, right, which is sigma in the denominator. So I will multiply both sides by sigma. The nice thing about that is that these sigmas will cancel, and then we're going to be left with z sigma equals x minus mu. Now, the only other thing that we would do to solve for solve for x would be to add mu to both sides. And the nice thing that happens here is that these mu's cancel and we'll be just left with the x on the right-hand side. And so that's why we have x equals mu plus z times sigma. All right. I want to go back to this q-norm function because we hadn't used this in JASP just yet. The q-norm function is known as our quantile function. So Q stands for quantile, and it basically is going to give us a quantile of the normal distribution. So what z value is at this point in our normal distribution. For us, this function is going to return a z-score. The function kind of works very similar to the p-norm function, but instead of spitting out a probability or a proportion, it's going to spit out a z-score. Instead of taking a z-score, it's going to intake or as an input have a probability or proportion. So I'm going to have q norm. I'm going to get the proportion that's represented by the area under the curve. That's what this p is going to be. I'm going to have a mean of 0, standard deviation of 1 because we're in a standard normal distribution, and we're still going to use the lower dot tail equals true if our area represents from some z value and all the values to the left of it, right? So the lower tail of the distribution. And then we can adjust this to get the upper tail of the distribution or from that z value and including all z values to the right or z values that are greater. Big difference here, once again, is P is that proportion of probability, which is the same thing as the area under the curve, that shaded area that we're going to be interested in. Let's look at an example. It says a researcher interested in STEM education gave students participating in an art program, they gave those students a math standardized test with scores that are normally distributed with a mean of 78 and a standard deviation of 8. I made a note here that the range of that test, so that test goes from a minimum of 45 in the population to a maximum of 105. All right, but the mean of that normal distribution is 78 with a standard deviation of 8. All right, so if this is a normed reference group, that is what we get from that norm, from that norm group. What we want to find out here is which score corresponds to the 75th percentile, because this researcher knows or hopes that if students participate in this art program, then their math score should actually be above the 75th percentile. All right. So we want to know what score corresponds to the 75th percentile. Well, the 75th percentile on this normal distribution is the area under the curve from the lower tail all the way up until the total area under that curve is 0.75, right? And so if I were to draw a normal distribution, I know that I would shade more than half of that distribution, right? Because half of the distribution is 50%, and I need to go up a little bit more. So if I drew my normal distribution, I would say that about 75% of that distribution, starting with the lower tail, because percentiles represents 75% or less. So I'm going to start with that lower end up until I get to about 75%. I know it's above the mean because the mean is at the 50th percentile, because the mean equals the median. So I've shaded in this area here. I need to find the X, the score that aligns at that specific point right there. I know that my lower tail equals true. If I use that for 0.75, that's going to give me my value. I need to find the Z that corresponds to an area under that curve on the lower tail being equal to 0.75. And so let's find that Z score, right? Well, for me to find that Z score, I'm going to use my Q norm function that corresponds with the area on the left side of the normal distribution equaling 0.75. So I know my probability equals 0.75. Since I'm finding a Z-score, I know the mean is 0, the standard deviation is 1, and I know it is on the left side or the lower side of that distribution. So I'm going to have lower.tail equals true. So we're going to go to JASP. I have my R console already up there. I'm just going to clear out my output. And now I'm going to write that function. It is Q norm. I have 0.75. I have a mean of 0, a standard deviation of 1. And I'm going to have lower.tail equals true. I close that parenthesis. I click run code. And I get 0.6744898. This is what Z equals. This is what Z equals. Now that I know what Z equals, I can go and proceed forward to find my X. So I have that from JASP. Now let's convert Z to X. Well, we have this formula here that X equals mu plus Z sigma. Mu and sigma were given in the initial problem, right? I think mu was 78 and sigma was 8. And we've just found Z to be 0.6744, so on and so forth. So I'll put those values into my formula. I can use a calculator or I can go to JASP. Actually, let's go to JASP. You can use JASP just as a calculator. So I'm going to do 78 plus 0.6744898 times 8. I'm going to click run code, and I get to approximately 83.4. All right. And so if I go back to my notes, We get 83.4 if I round that to one place after the decimal or to the nearest tenth place. And so a student must score at least or at 83.4 in order to be at the 75th percentile. So they need this score to be at the 75th percentile, 83.4. Let's look at another example. All right, we're going to stay with the same normal distribution, but this time I want to know which score would place a student in the top 10% of scorers, right? The top 10%. Well, I know I have a normal distribution once again. The top 10% would be the area under the curve from some value on the top side, the right side of that graph that constitutes 10% or a proportion that's equal to 0.10. So if I were to draw my normal distribution, this would be the area that I'm interested in, right? It's 0.10. Our goal in this problem is to find out what this value x here would be. We know the proportion, and we also know that we're going to use lower.tail equals false because we want the upper 10%, the top 10%. And then I'll know that once we get this score, you have to have at least this value in order to be in the top 10%. All right, so I'm going to go to use my Q norm function. I know that my probability is 0.10, but this time I'm going to have lower.tail equals false. And so I'm going to come over here to JASP. I know I'm going to have 10%. Now we always change that to a decimal, so that's 0.10 or 0.1. I'm going to have a mean equal to 0, a standard deviation equal to 1, and I'm going to have a lower.tail equals false because I want the top 10%, not the bottom 10%. Okay? I'm going to run this code here, and I get a Z of 1.28. Now, let's say that I said, let's use lower.tail equals true. How can I adjust this code to get this same value if I wanted to use lower.tail equals true? So let's say that JASP was not able to actually give me the lower tail, right? How can I adjust this code to use lower.tail equals true? Well, I'll tell you, right? If I go back to this picture, that's the last one. If this top area is 0.10, then this lower tail, this other part of this tail, would be 1 minus 0.10, right? And 1 minus 0.10 is 0.9. So if I wanted to, I could adjust this code by changing this to a 0.9 and doing lower.tail equals true. I'll run this code and you're going to see that I get that same value. All right. You don't always have to think like that. But when we were using those tables, so historically when people were using those standard normal table, we would have to do manipulations like that in order to get the correct area. And as I said in the last video, some of these are the default. So I can adjust this code in so many different ways so I don't have to type all of this stuff each and every time. I just wanted to point out that you can get a little bit more, if you get comfortable with this Q norm and this P norm function, you can do away without having to type in so much to get this done. Since our focus is not on statistical programming in this course, I'm not doing all that, but do know that you can adjust things to make things a little less tedious. But I just wanted to point that out. I think I always find things like that very interesting. All right, but we have our Z-score that aligns with the right tail or upper tail probability of 0.10 or proportion of 0.10. And so now what we have to do is convert that Z back to an X by using that formula X equals mu plus Z sigma. Remember, our mean was 78, our standard deviation was 8, and we just found that Z value. You can put that in a calculator or in JASP, and you're going to see that you get approximately 88.3. So this means that a student needs to score at least 88.3 in order to be in the top 10% of scorers, right? To be in the top 10%. I'm going to do just one more quick example because we're going to actually use this type of thing to find some values when we start doing statistical inference, which is the next piece in our course. And so it says, what z-scores separate the middle 95% of observations in a normal distribution from the other 5%? Remember that empirical rule? We said that approximately 95% of the observations are within 2 standard deviations. So we know that our values are going to be close to -2 and 2. Remember that stuff about unusual scores versus usual scores, right? Well, if I want to know the z-scores that separate the middle 95% from the other 5%, I know that I need to look at where the area under the curve of the middle constitutes 95% of that distribution, or proportion equal to 0.95. And then remember that the other not shaded region constitutes 5%. And I know that because the whole area is 100%. And if I do 100% minus 95%, or 1 minus 0.95, I'm going to get that 5%, or 0.05. Now, the stuff that's left over, just to make a point here, we can find out how much area those are by dividing that 5%, or that 0.05, by 2. And we know we divided by 2 because these are symmetrical or congruent areas, since our graph is symmetric. So if I take 0.05 and divide it by 2, I know that this unshaded area on the left tail is 0.025, and the unshaded area on the right side is also 0.025. And these are the values that I'm going to focus on to answer this question, right? And the reason for that is because our Q norm function, in the same way as our P norm function, focuses on values on the tail ends. It doesn't focus on those middle values. It focuses on values from a point to a tail, right? So if I want to know the z-score that separates this bottom shaded region from the unshaded region, then I'm going to use this 0.025, and I'm going to use lower dot tail equals true, right? Because this is on the lower tail, right? So I'm going to go to my Q norm to get that z-score, 0.025, lower dot tail equals true. And to get this z-score, I know that the area from that value covering all those values that are greater is 0.025. So I'm going to use my Q norm function. Now I'm going to use 0.025 again, but I'm going to use lower dot tail equals false. All right. And so if I go to Q norm here, I'm going to do 0.025. My mean is 0. My standard deviation equals 1. And lower dot tail equals true. Now remember, if I look at this graph, that 0.025, if I were to look back at that graph, this z-score is going to be negative because 0.025 is a negative value. So I should expect a negative value here. And then this is on the other side. These are symmetric areas. This is a symmetric graph, so these are congruent areas. And so this z-score is going to be positive. And in all actuality, they're the same distance from 0, since this is symmetrical. So I should get a positive and a negative of the same value. All right, let's go to JASP. Let's run this code. And notice here, I get a negative 1.96 approximately. So I should expect, when I do Q norm and I do the upper tail using that same probability of 0.025, lower dot tail equals false. Notice here, when I run my code, I'm going to get the positive. So if I go back, I will see that z equals negative 1.96 here, and z equals positive 1.96 here. All right. So that empirical rule was a bit of an approximation, right? 95% of observations are within 2 standard deviations. It's approximately, it's actually 95% of observations are within 1.96 observations. Standard deviations from the mean. All right. And so this is kind of inverting what we did in the previous video that we looked at for normal distributions. And so notice the difference, right? What we were doing before, we were starting with X and getting a proportion or a probability. But here, we're starting with a proportion or a probability, and we're going back to X, getting the value in our original variables units, or their scale. All right, we're going to stop here, and I think we'll look at one more concept related to normal distributions. We'll get there next time.